Okay, a couple of definitions for you as we begin the next section. Two events are said to be independent events if the fact that one event happening doesn't change the probability of the other. Okay, so for example, I'm going to, I don't know, say flip a coin. Okay. What happens on the first flip of the coin makes no difference or has any bearing at all on the probability of getting either result, heads or tails, when I flip a coin the next time. Okay. Those events are independent. If events are not independent, then probably not shockingly, the events are considered to be dependent. So let's take a look real quick at 4 quick examples. So independent or dependent, you roll 5 dice. So does what you get on one of the die have any impact at all whatsoever on what you roll on any of the other dice? The answer there should be no, there is no impact, and so these events are independent. You are dealt 5 cards from a deck. Okay, independent or dependent. So when you give someone a card from a deck, okay, notice that instead of having 52 cards in the deck after you've given them the first card, then there's only 51, and then 50, and then 49, etc. And so the probability of getting a certain card continues to change. It's 1 out of 52, then it's 1 out of 51, and 1 out of 50, etc. So these are dependent. You have 2 children in 2 separate births. The events are the first is a girl and the second is a girl. Well, there has, again, no influence whatsoever on what you have the first time versus the second time in terms of kids. So those are independent. And I've already mentioned flipping a coin. No coin flip impacts any other coin flip. Okay, once you flipped it, it's like basically starting back over at ground zero and going from there. So what happens when we want to calculate the probability of multiple events taking place? Okay, so 2 or more, what we do is we multiply the probability that each event happens in succession. Okay, so we've got lots of things taking place. Again, it could be 2, it could be 20. It won't be 20, but it could be. And we're going to multiply those probabilities of those events happening. Okay, and we look at them as individual events and just continue to multiply. So let's start here with example 4. You pick 3 cards from a deck. What's the probability they're all kings if the cards are replaced after they are picked? So in other words, you deal a card and you put it back in the deck and you shuffle again, okay? And then you deal a card and you put it back in the deck and you shuffle again. So we are looking for the probability that we get a king and a king and a king. Okay, we're picking 3 cards again in a row. So there are 52 cards in the deck and 4 of them are kings. So the probability you'd get a king on the first is 4 out of 52. Then we're going to multiply. Remember, you put the card back, so the probability we get a king again is still 4 out of 52. And similarly, the third time around. That ends up being 0.0005 whenever you round that. Now, one quick note that I want to make on your calculator, okay, on your calculator, you probably got something like this. Hold on here, I'm just typing it in so that I've got you probably saw 4.5516 and a bunch of stuff, and then this little e negative 4. Okay, this e negative 4, okay, this part right here, that is your calculator's way of writing scientific notation. So what that says is 4.5516 times 10 to the negative 4th. That means take this decimal point and move it 4 spaces to the left. Okay, so you fill in with some zeros. And then I'm going to round this 4 up to a 5 based on what's there. Okay, do pay attention. Don't just write down 4.5516. Remember, probabilities cannot be bigger than 1. It's impossible. All right, so pay attention to stuff like that. If you get an answer that looks like nonsense, chances are it's just because it's a little tiny number and your calculator is using scientific notation. All right, example B, you pick 3 cards from a deck. What's the probability they're all kings if you are not replacing the cards after they're picked? So this time we still want the probability of a king and then another king and another king, but this time no replacement. So the likelihood you'd get a king the first time is 4 out of 52, okay? But then you leave that card sit out of the pile, out of the rest of the deck, okay? So of those remaining 51 cards, how many of them would be kings? Well, 3 of them, because you gave away one already, okay? And then out of those remaining 50 cards, there would be 2 kings left in the deck. And we multiply all those together, and this time we get 0.0002. And again, watch for that scientific notation on your calculator. All right, you roll 5 dice. What's the probability you roll 5 even numbers? Okay, we want 5 even numbers. That's an even and an even and an even, etc., etc. So on a dice, there are half of the numbers even, 2, 4, and 6. The others are the 1, 3, and 5, of course. You can write 3 out of 6. I'm going to write 1/2 every time. And on your calculator, this will be a lot shorter to type that in as 1/2 or 3/6 if you'd like to the 5th power. That will give you 0.031 as the probability. And last but not least, for this example, you roll 5 dice. What's the probability you roll the same number on all 5 dice? Okay, the same number. So this one's a little different, but I want you to think of rolling the dice like one at a time, okay? It'll help. So when you roll the first dice, does it matter what you get? I hope you're saying, no, really wouldn't matter what I get, okay? So on the first dice, basically, you can roll any number that you want to roll. But now, if you're trying to get the same number on all the rest of the dice, you can't just roll anything. You have to match what you just rolled on the first die. Okay, so let's say, for example, you rolled a 3, okay, on the first die. Now you have to roll a 3 the next 4 times. And so the probability you would roll a 3, for example, would be 1 out of 6, 1 out of 6, 1 out of 6, and 1 out of 6, which is, again, probably in scientific notation on your calculator, about 0.0008. Okay, so this one has to match die number 1. Okay, whatever that happens to be. So again, you got to take just a little different perspective there. But again, I think if you stop and think about it for a minute, or actually go grab one die and just say, hey, instead of 5 dice, I have 5 rolls and I have to get the same number every time, I think you'll see that that works out.